All right, in this last video, we're going to look at problem number 5 on radial fields and the inverse square law. So part A says describe the vector fields R, which is xi plus yj plus zk, and r hat, which is the vector R divided by this scalar R, where R is the square root of x squared plus y squared plus z squared. Okay, so first notice that the scalar R is just the magnitude of this vector R, and it's just measuring the distance from the origin to the point x, y, z. And so this vector r hat, this is just the unit vector in the direction of this vector r. Okay, so to get a feel for what this vector r is doing, okay, if I draw this position vector from the origin to this point x, y, z, well, this position vector really is just r. It's xi plus yj plus zk. But for r, we are going to draw this so its tail is located at the point x, y, z. So here would be our vector r, right? So it just points radially outward from the origin. Its tail is at this point x, y, z. Okay, so this is really the three-dimensional analog of what we saw in problem number 1. We discussed the radial vector in R2. Okay, so then this vector r hat, as we noted, this is just the unit vector in the direction of the vector r. All right, so let's go ahead and plot these on math3d.org. So here in blue is just our vector r. So you can see these vectors are all pointing radially outward, right, from the origin. And as we move further away from the origin, the magnitude is growing, right? So we can see that, as you get further away, those arrows become longer. Okay, now here's the vector r hat. It's just this field of unit vectors. They all point in the same direction as the blue vectors. They're just unit length. Okay, so that all makes sense. Now, in the case of the radial vector in R2, we looked at that family of concentric circles centered at the origin and noted that those radial vectors were perpendicular to those circles. Well, here we could add in, say, a family of spheres, okay, and these radial vectors are perpendicular to these spheres, as you can see there. Okay, so that's quite nice. All right, so now let's go ahead and look at part B that deals with the inverse square law. This is a number of fields from physics. So examples is gravitational fields and electric fields. These are two such examples that obey what's known as an inverse square law, okay, which says that the magnitude of the field at the point xyz is proportional to the inverse square of the distance from xyz to the origin. And the origin in this context is sometimes referred to as a source, okay, for the field. All right, so now the distance from the origin is just this scalar r, okay? So to say that the magnitude of our vector field at the point xyz is proportional to the inverse square of this distance is really saying that this magnitude is equal to some constant of proportionality k divided by the square of that scalar r. Okay, so now looking at part 1, this is on a gravitational force. And so here, okay, I have two point masses. So point mass little m and a point mass capital M. Think about, say, capital M as the point mass located at the center of mass of the Earth, something like that, okay? And the Earth is going to exert a gravitational force on, say, you or me, right? Something with mass little m, okay? And the gravitational force, this is a gradient field, okay? And the potential function is this function we'll call u, which is g capital M little m divided by that radial distance r. And here, the capital G, this is Newton's gravitational constant, which is roughly about 6.67 times 10 to the negative 11th Newton meter squared divided by square kilograms. Okay, and again, just the r is that distance, in this case, between the masses. Okay, so say the distance from U to the center of mass for the Earth. Our job is to compute this gravitational force F, uh, given the fact that it's a gradient field. Now here, this is just a convention commonly adopted in physics, to stick a negative in front of the gradient of this function u. It's just a sign convention which, after we actually do the computation, will make a little bit more sense as to why that choice is made. But let's go ahead and do the computation. So our function u, this is the potential function. It depends only on this quantity r, so it's gm little m. These are all constant, so they're really the variable part of this expression is just in the denominator. Now I need to take the gradient of this function, and I could just write everything in terms of x, y, and z and take derivatives that way. But it's actually a lot easier to do the following. Okay, we can compute the derivatives of that quantity r as just a side calculation and then just use the results in this gradient computation. It makes things a heck of a lot easier. Okay, so here are the results. So if I differentiate r with respect to x, I simply get x over r. Let me show you why. It's not a hard calculation, but again, this is a nice thing to just get out of the way, um, because it'll make the calculations we're about to do a lot simpler. So here I'm differentiating this quantity, x squared plus y squared plus z squared, under a square root with respect to x. So since I'm differentiating a square root, I'm going to get 1 over twice the square root. And in this case, the inside is this sum of squares. Then from the chain rule, I have to multiply by the derivative of what's inside with respect to x, and that's just going to give us 2x. And you can see here the 2's are going to drop out, and this square root term in the denominator is just r itself. So there you go, it's x over r. And of course, the same calculations show that the y derivative is y over r and the z derivative is z over r. Okay, so now with that in mind, let's go ahead and compute the gradient of this potential function u. So the gradient of u, this is going to be the partial of u with respect to x for the I component, the partial of u with respect to y for the j component, and the partial of u with respect to z for the k component. All right, so for the x derivative, okay, notice that u I can write as gm little m times r to the negative first power. So to differentiate this, just use the chain rule. Okay, I'm differentiating r to the negative first. So that's going to give us negative r to the negative second, or in other words, I'm going to get negative g capital M little m over r squared. Then the chain rule says multiply that by the derivative of what's inside, which is just r, with respect to x. Okay, now we can do the exact same thing for the y and z derivatives, and they look very, very similar. So this is going to give us the partial r, partial y, and then I'm going to have minus gm little m over r squared, and then this is partial r, partial z. And now go ahead and just punch in these expressions for the x, y, and z derivatives of r. Okay, also go ahead and factor out that minus gm little m over r squared. So for the x derivative of r, that's just x over r. Then the y derivative, that'd be y over r. And the z derivative, that'd be z over r. Okay, so let's go ahead and factor out that 1 over r. So I get minus gm little m over r cubed times this vector x, y, z. Okay, great. So now our force vector F is going to be what? Well, we said that it's the opposite of the gradient of u. Okay, So by making the choice to put the negative in front of this gradient, you can see now it's going to make this a positive. So I'm going to get what? Well, gm little m over r cubed. And what is this vector right here? Oh, well, that's just the vector r, right? So I have this times the vector r. Okay, so that would be one way to write the expression. What would be another way to write the expression? Well, notice that if I just take out a factor of r, or in other words, just sort of backtrack really to this step here, but I'll do it off to the side here nonetheless. If I write it as gm little m over r squared times the vector r divided by r, this vector r over scalar r is just r hat. So I can also write our force vector as gm little m over r squared times the vector r hat. Okay, and then lastly, I'm going to add, we could also write this, of course, in terms of x, y, and z. So what would that look like? Well, this expression out to the front, this is going to be gm little m over, so what's r cubed? Well, if r is this square root term, if I cube it, I'm going to get x squared plus y squared plus z squared to the 3/2 power. And then I'm just multiplying here with this vector x, y, and z. So all of these, of course, are equivalent. Okay, now it's this one right here that actually makes the fact that this gravitational force obeys the inverse square law really easy to see. So I'll make a little note here off to the side. If I take the magnitude of our vector f, okay, if I use this expression here, the nice thing is that r hat's a unit vector. Okay, and so it's really this stuff out front that's telling me what the magnitude of the vector is. I say taking the magnitude here, I'm going to just take this scalar times the magnitude of r hat, which is 1. So this is just going to be gm little m over r squared. And now I can see, yeah, the magnitude of my vector is proportional to the inverse square of that distance from the origin, right? And that constant of proportionality is just this gm times little m. So this implies that F, gravitational force, obeys an inverse square law. Okay. All right, so that does it for the first one. Oh, I guess I will just mention here in passing this choice of the minus out in front. We'll notice, you know, if I'm thinking about this point mass, capital M, as the thing exerting the gravitational force. So again, I think about, like, say, the Earth exerting the force, say, on you. Okay, then the force F is directed towards capital M. And so I'd want that to come out to be a positive expression. And so by putting the negative in front of the gradient, it makes the whole thing positive. Okay. All right, cool. So now let's go ahead and look at the second part there. This is a little bit shorter. This is about electric fields. And here it says the electric field E created by a source charge Q naught is a radial field that satisfies an inverse square law. Okay, the strength of the field at the point XYZ is given by K times Q naught divided by R squared, where K is Coulomb's constant, about 8.98 blah 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 times 10 to the 9th Newton meter squared divided by Coulomb squared. It's okay if these units and some of these terms are not familiar to you, but in any event, again, R is just this same quantity as before, distance from the point here, XYZ now, to the source. Our job is just to write down an expression for E. And the point here is that Well, this is a radial field and it's satisfying this inverse square law. So this is what we know. We know that the magnitude of our electric field is equal to kq0 divided by r squared. And we also know that the field is radial. Okay, so in other words, if we're looking at some point, say right here, then I know that the electric field is going to point radially outward. So just take that position vector and move it outward. Except then, of course, you're going to have to scale it by, so if this is, say, R, then the actual field itself, might look something like this. Okay, but the point is that it's a multiple of this radial field R. All right, so here's the idea. E, we know its magnitude, right? It's right here, and we know it's pointing in the direction of this position vector R. And so what I can do is just take kq0 divided by r squared, its magnitude, and multiply that by, well, the unit vector in the direction of r. So in other words, I could write that as just r hat. Or if you like we did with the gravitational force, I could write this as r divided by scalar r, and so I could get the quantity kq naught divided by r cubed times the vector r. Okay, these are equivalent. All right, well, that's going to do it for this problem and for this section. Thanks so much.